So we now come to our first method for finding root of a function, and it's really the most well-known method and the basis for all kinds of more advanced methods in numerical analysis. It's Newton's method, and the basic idea is a really, really fundamental one, which is also very easy to state. Quite simply, we don't know how to solve a nonlinear equation. We don't know how to find an inverse function in most cases, just by writing things down. So what we'll do is we'll replace the problem we don't know how to solve with a linear one that we do know how to solve, and hope that it's a good enough approximation to work. So in terms of the mathematics of this problem, here's our original nonlinear problem, finding a root of this function. Okay, we don't know really how to solve that explicitly, so what we do is we replace it with the linearization of the function. So we know that it's not exactly the same thing, but we'll leave it as an equality anyway to define what it is that we're going to do with it. So in other words, we can't really solve the original problem. We're going to solve this linear approximation instead. So that's an easy enough problem to solve. You just rearrange and find the x, and we get a formula for the solution of that linear problem. So there's a very simple way of interpreting this graphically. So here's our function. Let's say we have a value of a here. So this point on the curve is the point a, f of a. Right? I should write that this curve is y equals f of x, the original function. And now what we do is we construct the linearization, the linear approximation. That's the tangent line at this point. So that's our linearization. Okay, and then this value here, the solution of that linear problem, is our x. So that's the solution of the linear problem. And it's not exactly the same as the true root. But you'll notice in this case that it is closer to the root than the original point A was. So if all I had was the function and the point A, I've just found a point which is closer to the root than A itself was. So that suggests that we should turn this into an iterative method. Given one guess at the root xn, we want to get a better guess. So we'll put A equal to xn in the linearization. So in other words, xn is the linearization, the center of the linearization, or the point of tangency, if you like the graph better. And then xn plus 1 is the solution of that linear problem. So we just replace the symbols in the formula we had above, and this formula defines the Newton iteration. So given a function f of x, we need to start with an initial guess x0. Then we set n equal to 0 in the formula, and that tells us how to find x1. And then we set n equal to 1, and that tells us how to find x2, and so on. So for example, here's a function which is a quadratic polynomial. So to use Newton's method, we also need the derivative of f. So it's easiest just to write that out here. 2x minus 2, or 2 times the quantity x minus 1. Okay, so x0 is equal to 2. So x1 is equal to, go back up to the formula here, set n equal to 0 in that formula. We get x0, which is 2, minus f of x0, that's 4 minus 3, divided by f prime of x0, that's 2 times 2 minus 1. So we get 2 minus negative 3, so that becomes a plus 3 over 2. And that's 7 halves. All right. Now we have x1. Let's compute f of x1. F of x1 is 7 halves squared minus 2 times 7 halves minus 3. So that's 49 over 4 minus 28 over 4 minus 12 over 4. So that's 9 over 4. F prime of x1. I'm just computing the things that I'm going to need in the formula to find x2. F prime of x1 is 2 times 7 halves minus 1, which is 2 times 5 halves, which is 5, but I'm going to write that as 20 over 4 because it will be easier in the next step. Okay, so now finally we can plug into the formula, the Newton iteration formula up here with n equal to 1. So we get x2 is x1 minus f of x1 divided by f prime of x1. So it's 7 halves minus 9 twentieths. So that's 70 twentieths minus 9 twentieths is 61 over 20. Okay, etc. Just to point out, in this problem, f of 3, right, this is just a quadratic polynomial. You can factor it easily. F of 3 is 9 minus 6 minus 3, which is 0. So 3 is a root. So we started with a guess of 2. x1 was 7 halves. That's 3.5. x2 is 3 plus 1 over 20th. That's 3.05. So in fact, we are getting closer and closer to the true root in this case. Which leads us to the subject of convergence in general. So first of all, if we write down the iteration formula again, we notice that if the sequence does converge to a limit, call it x star, right, then if we let n go to infinity on both sides of this equation, we get this. And so, of course, x star subtracts off of both sides, and we conclude that f of x star must be 0. We could have a problem if that denominator is 0. As we know, if that denominator is 0, then the root finding problem is ill-posed. It's infinitely ill-conditioned anyway, so we knew that that would probably cause us some unhappiness. So if we ignore that ugly case, certainly if the sequence converges to some limit, that limit must be a root. So if the sequence converges, it converges to a root. But we can actually be more precise about that. So now we're going to define, we have a sequence of iterates x1, x2, x3, and so on. Let's say r is an exact root of the function. So by solution here, I mean root of f. So then we can define the errors as the difference between the xn and the true root. So if we start from the basic Newton iteration, okay, subtract r from both sides of that, and then we do a substitution where xn is equal to en plus r from here. Okay, so we get this line here. And now we can see that on the xn plus 1 is just, or I'm sorry, the xn plus 1 minus r is just en plus 1. Xn minus r is just en. Okay, and now we're going to do Taylor series expansions for the numerator and denominator of this thing. So the idea, what we're thinking is that the errors in this sequence will get small, and so therefore we're justified in taking the Taylor series around the point r. So that's the numerator. Now the denominator, we're taking a Taylor series of the function f prime. So that means that everywhere we had an f above, we just put in an f prime. Okay, so I'm going to continue this derivation in the second part. I'm just trying to keep the video length on the shorter side here.